Thrilled today to welcome Haiwen Chu as our speaker. Haiwen is a research manager for the English Learner and Migrant Education Services content area team at WestEd. He serves as a principal co-investigator on the National Research and Development Center to Improve Education for Secondary English Learners, funded by IES. And Dr. Chu draws upon his experiences as a high school mathematics teacher to design educative curriculum materials to expand the capacity of mathematics teachers across the country to challenge and support their students who are bureaucratically designated as English learners. And he's going to speak more about that particular label. Prior to joining WestEd, Haiwen taught mathematics to high school immigrants and English learners in New York City, where he created projects connecting students' lived experiences. While in New York, he also taught graduate courses to in-service math teachers, conducted research about culturally relevant mathematics pedagogy. It's clear from reading Haiwen's work that his heart is in the classroom, and particularly in the mathematics classroom. And so we're grateful he can join us today as the first presenter in the MLRC Speaker Series. Look forward to hearing more about his work. Thank you, Dr. Chu.
Thank you for that kind introduction. It's greatly appreciated that we have this opportunity to take a look at this question, right, of how do we engage multilingual learners in deep mathematical work. So this webinar has the following structure. We are going to spend some time unpacking what ambitious mathematics learning is. Then I'm going to offer you some evidence of what that student learning looks like based upon our field trials. And then we want to leave plenty of room at the end for questions and answers. And so feel free to throw those questions in the chat as they come up. And at the end, we will pause and address them sort of coherently. All right. So one title for this presentation is actually Reimagining and Amplifying Mathematical Participation, Understanding, and Practices, or RAMP UP for short. And I will describe how that is actually the name of a summer bridge program that we have been field testing for the past 3 summers in different locations across the United States. But let's begin more broadly. With this issue of what is ambitious mathematical learning, specifically for students who are bureaucratically designated as English learners, who are part of a broader group of multilingual learners that includes students who were never designated as English learners but are multilingual, as well as those who were formerly in the category and now sort of reclassified as fluent English proficient. I may say the term English learner to mean students who currently have that designation. But more broadly, multilingual learners is the umbrella term that we like to use to acknowledge the sort of diversity that students bring into the classroom in terms of their language practices. Unfortunately, there currently are significant barriers to access and achievement with regard to secondary mathematics in particular. And a lot of this is systemic in the sense that our course sequences are largely sequential, and the requirements, especially for English learners in terms of language, sometimes treat language as a prerequisite rather than as the medium through which mathematical understanding can be developed. And the situation quickly becomes even more bleak when you consider the orientation of curriculum. Instructional materials often are in a transmissionist mode where what they are repetitive practice of procedures learned precisely for the problems that they are suited to solve. What is typical is you will have students practice the same procedure algorithm over and over again, but you've only given them problems for which the procedure works, and so it's not clear what you would do in a different scenario. What we really want to move the field toward is more toward the curriculum oriented as a thinking tool so that educators can really invite students to develop their own approaches and then progressively formalize them and apply them to new problem settings. And so what you'll see in today's presentation as I share the student work will be that precisely, it is the students who are generating ideas. It is the students who are generating approaches. And as they are doing so, they are developing the language with which to negotiate those ideas and also to express the understandings that they've achieved by the end of the work. And so we solidly fall on the thinking tool side in terms of developing instructional materials that really require multilingual students alongside all of their classmates to develop and create new mathematics. And so indeed, our approach to ambitious math learning is founded on three key ideas. The first is we need to focus on the concepts that motivate and drive procedures rather than the repetitive application of procedures. And so this means focusing on cross-cutting concepts that unite the secondary mathematics domains of algebra, geometry, and statistics. And we'll see some examples of what that is shortly. Well, what that means then in the classroom is that students need sustained opportunities to engage with each other as they develop that understanding. There's an old saying in the Dutch tradition of realistic mathematics education, which is caution, there's ready-made mathematics ahead. We do not want students to receive the mathematics, rather we want them to create it. And the way that they create the mathematics is in interaction with their peers, is in interaction with the teacher, and is through what we call quality interactions that add up to participation over time. And so what this means is that the language opportunities that we offer students need to enable them to explore concepts deeply and also to engage in mathematical practices. Mathematical practices are precisely those ideas, those higher order thinking approaches that enable the development of new mathematics. And so language is necessary both for the development of concepts and for engaging in mathematical practices. And so to elaborate on each of these a little more, you will see that there actually is some nice overlap between the conceptual focus, which is about ideas and practices and engaging problems, and the language then necessary to develop it. And so what we want to see and hear in classrooms is talk that is sustained, talk that actually is in depth and expands upon at breadth students' ideas and reasoning. And so then that means that they will engage with each other in interactions that are reciprocal, that actually are characterized by a genuine back and forth negotiation of ideas as they are figuring out new mathematics together. And so what's going to happen is over the course of a week, over the course of a unit, students' participation changes over time. It matures and it develops, and they develop greater autonomy as they develop deeper understanding of the mathematical ideas. And so looking at language, what should happen is the student's language changes and grows. It grows from more dialogic back and forth ways of using language to more monologic forms, from more peer to more authoritative ways of using language, and then from more everyday uses of language to more technical uses of language. Often with the best of intentions, we supply students with the technical language of mathematics without adequately giving them time to make the connections from everyday forms of language to those more technical types. And so this is the vision of ambitious mathematics learning that we need to enact for, which will benefit all students, but the participation and the language in particular are critical for multilingual learners precisely because they need both the opportunities to participate and the rich choices of language that enable them to do the mathematics and explore the mathematics in a generative way. And so what we really want is an integrated approach to thinking about the design of instruction and thinking through what those opportunities are. And so what that looks like is developing the conceptual understandings, which are the ideas that undergird procedures, connecting those to the practices that we want students as emerging mathematicians to engage in. And then understanding that the role of language is going to be critical for them to do all of those things. We view these, however, as inextricably interwoven rather than three separate domains. Okay, so just to elaborate a little bit further on this notion of quality interactions, once again, what you want to hear is individual students are expanding upon ideas in depth and at breadth, but they're also having a dialogue. They're also discussing and building on each other's ideas, challenging them, and ultimately revising them. And then you want that substance to be about the mathematics. You want that substance to really focus on developing mathematical ideas. And so that's something that you can actually observe in a very short time frame just by sitting with students and listening to their talk with one another. And so that is what we mean by quality interactions and the sort of centrality of talk as the vehicle for thought as students explore mathematics. More broadly speaking, in terms of language, we need to offer students amplified opportunities to engage with and use language, not to simplify or take away the complexity and richness of different texts. So they should be reading amplified texts that are engineered to facilitate access and discussion, right? Because we don't view reading as a solo act. We view reading as something that you initially can productively do with a partner as you begin to unpack the meanings of texts and you make sense of what you're reading. We offer them in the moment choices of formulaic expressions to engage in mathematical practices, like looking for structure and making use of regularity. We offer formulaic expressions because they are what connects different ideas to one another. So for instance, if students are comparing two rates of speed, they might benefit from language such as, I think so-and-so is faster than such and such because, right? I think a student late for class is faster than a student in line for lunch because they're in trouble and they don't want to be marked super tardy. And so the expression connects many ideas and can be used over and over again in a variety of settings, right? It's not just a fixed right or wrong answer to that language that connects ideas. So that's what we mean by formulaic expressions. And then in mathematics, the expressions that are then about practices quickly require that sort of flexibility for it to be generative. And then finally, the bulk of the work I'm going to share with you today is actually not about the talk. It's actually about students' mathematical writing, because we too often do not see the fruits of their labor in terms of their written work products. And so we also think that it is critical that there are opportunities for students to then write to demonstrate their achieved understandings. That said, we always say that writing is not an event, okay? Writing is a process, not an event. It is something that is happening throughout the week. Students are writing, they're reflecting, they're reading each other's reflections, and then that culminates in the writing samples you're going to see, because those writing samples are the culmination of all of their explorations that involve much lower stakes forms of writing along the way as well. Okay, so that is the framing. Let's actually take a look at the present project, which has been, since 2020, we have been working to iteratively develop a 3-week summer bridge program for rising ninth graders, focused on multilingual learners, but actually enrolling all students, because we believe that mainstream settings are the most powerful for students to participate in. And so for 4 years, we had been working on the student materials. We have then also added a suite of educative teacher materials to facilitate their implementation of this curriculum. And this summer, we are conducting 2 pilot studies, one which is a randomized control trial with a sort of comparison group and a treatment group, and then another one that is a delayed intervention, RCT, which has 2 treatment groups, but one happening first compared to the staggered one in the second half of the summer. So what does ramp up look like? Well, it's 3 weeks, and the 3 weeks are organized into modules, and the modules are about central and generative ideas of mathematics that constitute cross-cutting concepts in mathematics. So specifically, the first module is about patterns. The second module is about networks and surfaces. That's what I will share with you today, some examples from. But the third module then wraps it all up and ties it all together, rather, because it is about the cross-cutting concept of equivalence, which is one of the central and generative concepts of school mathematics. What does it mean for two quantities to be, two algebraic expressions to be equivalent? It's different from solving an equation for a particular value of x. It actually would mean that they are completely equivalent for any value of x that is substituted. And so those are the sort of themes for the three modules. And as you can see, this is much broader than procedures. It really is trying to have students have experiences that indicate that mathematics is a coherent discipline rather than a collection of procedures or a course sequence that was invented in the 19th century and has not really changed since then. But that's another presentation. Okay, so let's dig into some student work. Let's dig into some examples of what students are capable of as they engage in the sort of mathematical explorations. And so the module, which is all about networks and surfaces, is about exploring how do you represent connections between people, objects, or things. That's the core idea of how do you create these networks of connections. And we chose this topic in part because social networks and other kinds of networks are an unavoidable part of everyday life now. And so whether it is the network of electronics that brings you to this webinar and me to you, whether it is the network that we have developed on LinkedIn in terms of our connections, or whatever kids these days actually are on. I don't know what social media kids are on these days, but there is this idea of what are the connections that you have. And even before, social media, there were always social networks in terms of families. And so a lot of what we begin with actually is students mapping out their social networks, their in-person networks of friends and family and the connections and the removes. And so it's that idea that we draw upon, that real world scenario that we then develop mathematical representations for. And so the idea is, right, as you can see in that little diagram, you can begin to make connections. You can begin to connect the different people in your life based upon their relationships with each other. And so that idea of how do you represent the connections between people is the sort of motivation for the rest of the module. But the module actually quickly goes from that relatable context to pretty sophisticated arguments, pretty sophisticated proofs of three types. The first type is, how do you prove something is impossible? That it's just not possible to do, right? There's no way to do it. I mean, it's one thing to not be able to do something, but how do you prove that no solution exists? This is one instance of what students engage in with these networks. A second kind of proof is a proof by induction, which is a powerful technique for building on different cases in order to generalize. And then the third kind of proof is the proof by exhaustion. How do you prove that these are the solutions and these are the only possible solutions that you can possibly create? And so, although we start with very relatable contexts, very quickly these become abstracted to mathematical representations where we have those points, those vertices you see being connected by lines or by edges. And that indeed is the topic of the first problem that we have students explore. We actually have them explore three impossible problems about how do you draw pictures that connect in different ways on a flat sheet of paper, different sort of scenarios. And so although it's grounded in a very realistic scenario or situation, it quickly becomes a more abstract problem where you're dealing with the representation of points connected by lines, or more formally, vertices connected by edges. And so there are questions like, if you have three houses and three essential utilities, can you connect all three houses to all three utilities without any of your lines crossing? Can you draw all of the handshakes among five people without any of the lines crossing? Can you draw four circles to represent four sets and show all possible intersections of those sets? And so we begin with these problems of impossibility in order to have students launch into generating a lot of different networks that they can draw immediately. And they're very engaged, and they discuss with each other, oh, we almost got it, but not quite. And actually, when they begin, they tend to draw houses very literally. You've got an igloo there, and you've got some sort of Flintstones type house. And you've got like, graphic representations of electricity, gas, and water, I guess. But then pretty quickly they abstract, and then they represent the houses and the other objects more as points or dots or vertices, and trying to find the connections. And the way that we stage the utilities investigation is we have them surface the assumptions that they're making, and they very quickly generate the idea that, well, this is on a flat sheet of paper, but what if it were more like the surface of the Earth, where you can actually go all the way around the equator, where you can go up to the North Pole and down again? And so they often surface the idea of Pac-Man, where you go off one side of the screen and then come back on the other side of the screen. And eventually they develop some other rules. And so after, this is after a week's worth of exploration, we have the students choose what they want to write about to demonstrate their understanding. And so at the end of the week, after a lot more investigations, one student wrote up her understanding of the utilities problem, some of the constraints, the fact that they were able to get 8 of the 9 connections, but then couldn't figure it out. But then they realized, wow, if we change our assumption, and we change the surface that we're working on so that there is this ability to go off one side of the screen and come back on the other one, then it is possible. Then it is possible to actually solve this problem.
So
It
it's
is actually
about
possible
Friday the
to
16th
create
until we have a room and
all those.
time. Let me see if I can. Okay. I was
Okay.
going to propose from like 9 to 12.
So now the students are able to identify the conditions that enable the solution to the problem. And so it may be a little bit hard to see. Let me see if I can zoom in a little bit. Now you have this connection that's going off to the left, and it's coming back. It's coming back on the right, and it's connecting the house to the electricity. And there's another connection going up and coming back around from the other way. And so the written product is evidence of what students are capable of after a week of exploration, when they've also looked at many other examples of impossibility. And so again, the written products I share as the culmination of talk, the culmination of investigations that are both individual and sort of students working with each other. And so what they're able to do by the end of that week in terms of written products is they're able also, for the handshakes problem, to systematically list out what should be all of the handshakes, and then to systematically say that they're missing something, because as the student notices at the end, they're trying to get 10, but they can only get 6 faces, 6 combinations of 3. And so it's impossible because 6 does not equal 10. And so we won't have time in this presentation to actually read the writing, but some of the key features here are they're setting up the frame, they are applying what they've learned about the properties of graphs, and then they are able to construct an argument that it is impossible because some other conditions are not met. This is similar to what another student did with the Venn diagrams problem. She systematically counted, and you see her listing there. There should be a total of 16 intersections across 4 sets, but they're only able to generate 14 of them, and so that is not possible. That is not what they're trying to achieve. And so once again, this is at the end of a week's worth of exploration and other activities that they are able to culminate in these kinds of proofs. But along the way, right, so I'm sort of giving you the spoiler at the end, right, that this is what they're able to do by the end. Let's talk a little bit more about what they did along the way in order to get there. And so one of the activities that we have them do, which is our version of having them engage in induction, in mathematical induction, is we have them co-construct. We have them engage in an activity called a Step It Up, where two partners, A and B, share a paper. And the idea is they are tracking the vertices, edges, and faces of the networks that they are creating, and they are adding to it, and then they are tracking what it is, and they're also talking about what they're getting. So I won't read you the transcript, right? But the point is, as they are going back and forth, as they are co-constructing a graph together, they are also going back and forth, counting things differently, and coordinating their representations. And so they're able to then construct, in this back and forth process, by the end, you have the shape that has 8 vertices, 9 edges, and 2 faces. And so where the secret sauce in our approach is what we do next, which is now that you have a graph, we have the students exchange their graph with another pair, and now their task is to deconstruct the graph, is to begin deleting pieces and then to track what happens there. The one caveat here is we want the graph to stay connected. We don't want, disparate points that are not connected to each other. And so when they do this, it actually enables them to track, to actually follow along what's changing with regard to the vertices, edges, and faces. What's happening here is they're seeing that as I remove one edge, I also lose a face. As I lose a vertex, I'm also losing an edge. If I delete 2 edges, I actually lost a vertex and a face. They're going back and forth. And then by the end, they've deconstructed a very complex shape, right? This was a shape that some other group had given them, into the essence of a polygon, right? And so what this all leads up to is being able to develop a formula for the relationship between vertices, edges, and faces. Because it turns out that those 3 quantities are always related in a connected network. And indeed, the way that we did this was we had the students generate examples. If you know there are 7 vertices and you have 3 faces, can you draw a graph that satisfies those conditions? What can you say about the edges? Similarly for those other cases that you see. And so the little post-its are students' examples that they created and then they posted in the relevant places. And then those formulas in red were the writing of a student who was able to say, well, I keep on getting 9 in the first row. I think that's 7 plus 3 minus 1. I think that's vertices plus faces minus 1. And so the students were able to develop the formulas because it turned out that even though the graphs looked very different, they all had the same parameter. They all had the same result in terms of the faces. And so what that is actually is one of the cross-cutting concepts of mathematics, which is the idea of an invariant, which is the idea of a constant that you can calculate for a given object. In this case, it's known as the Euler characteristic, and it turns out that vertices minus edges plus faces always equals 1 for a connected graph. And so the students were able to generate that formula and make the connection between the different parts while having an argument for why, right? Because the argument for why goes back to the induction. Well, basically everything's the same as 3, 2, 0, right? Everything is the same as it, because I can always deconstruct it and I can always reconstruct it. So all of these graphs are equivalent, and the constant, the invariant that I can calculate is the Euler characteristic. And so that's the piece that they actually went back to. So if we go back to their writing, that's the piece that they actually employed in their writing to say, well, you know, we really wanted 10 faces, but unfortunately, when we have that number of edges and vertices, it doesn't work with the Euler characteristic. We really wanted 16 faces for the Venn diagrams, but when you have the other parameters in place in terms of vertices and edges, it's right there, right? The number that you want, it doesn't work out because it doesn't work out. So it actually, they were by the end of the week, now that they had explored the Euler characteristic, they were able to then really get at these correct arguments. I mean, their logic is valid here. Their logic is sound here in terms of why something is not possible. And we also did give them choice about the kind of problem they wanted to write up. And I think that's actually an important feature, right? When they have that element of choice, when they've explored 3 problems and they get to choose which one they want to go deeper in, they tend to be more invested in their particular learning. I'll mention one more example. I'll mention one more example that is connected, and then that will bring us to a good place in terms of the presentation. So one additional example that was very surprising for students was, how do you find all Platonic solids? How do you generate all solids, all 3-dimensional shapes where each of the faces is the same polygon, the same regular polygon? And so in particular, we had students either build models or look at those now more and more ubiquitous plastic dice for board gaming as the sort of Platonic solids. And what they did was they developed different counting strategies for counting how many vertices, edges, and faces there are. So, you know, for instance, for the cube, often people think, okay, each face is a square, so that's 4. 4 times 6 for the 6 faces on a cube, that's 24. But wait a minute, I've actually counted all of the edges twice. So actually there should be 12 because each edge is on 2 faces, right? So this edge is on 2 faces. I've double counted. And so students come up with arguments for why there are only 12 edges because of double counting. And so they sort of develop these approaches and they are talking with each other about, is that right? Is it 60? No, it can't be 60. It has to be 30 because you're counting too much. And then some students were able to notice a surprising relationship. I mean, not only does this also sort of satisfy the notion of the Euler characteristic, but if you look carefully at the cube and the octahedron, those 2 rows that the student has circled, they sort of notice that the numbers are repeated, and they were able to say, oh, okay, why is it that those are repeated? What is the connection between the cube and the octahedron? It turns out that mathematically, those 2 shapes are dual to each other. Most students didn't fully realize the promise, but, you know, recognizing the pattern is the first step. The main argument that they were able to generate was why there can't be any more. There can't be any more in part because you can't have more than 5 faces, and you can't really have more than too many things meet, right? And so the fact that there's this symmetry in the table is an argument that there is not any other possibility there. Right. Okay, so that gives some examples then of some of the student work that is possible when these structures are put in place. And so here goes some broader considerations because yes, this was a summer setting, so it's a little different from day-to-day classroom settings. It really is beginning with things that students can make connections to, make analogies with, the sort of quick entry into a problem that they can immediately start tackling and immediately abstract into the representations. And so That said, we do need to create the participation structures that enable all students to participate. And so that's very carefully designing the idea that you have the students go back and forth, they build on each other, they're articulating their ideas, they're not just handing the paper back and forth. They're actually verbalizing what they're seeing and how they're visualizing those changes. That also becomes very important. We also want students to offer their ideas and their opinions and their approaches and ultimately co-construct. Now, that's a little challenging when it comes to writing, because writing, although we tried to make it as interactive as possible, is something that students tend to do individually. How we structured it is we had them give each other feedback and input along the way, and we had them draft throughout the week what they were thinking, what they were observing, so that it culminated in a more accomplished piece of writing. And so that's how there are those sort of structured opportunities around the writing. And then we did highlight sort of what are the kinds of moves that are helpful, right, in terms of listing out the examples, in terms of developing contradictions. But ultimately, we want to give students choice in how they express themselves and their understandings. We would never offer them like a script or like, here's the outline that you must use and fill in the blank. Because ultimately they need to own the ways that they use language. Okay, I think I'm out of time, but we did leave 20 minutes at the end so that there would be plenty of time for questions and discussion. And so I'm happy to offer that. And I guess we'll save some of the other slides for later. Okay, I'm gonna momentarily stop the share.